Sure.
Okay, so I'm recording now,
Mhm.
and I'm going to go back into the screen. Perfect. Okay, so you were asking me that every
Yes.
time that...
Yeah. So basically, when we are identifying into the dips in the time series that there could potentially be star spots, we can have several star spots, right? If they are placed, as we are looking at the magnetogram, if they are placed horizontally, right on top of each other. So.
Yes. So for example, this big dip could be either... This is like the deepest, like the deepest dip. There is another one here. This could be either a massive spot, single massive spot, or several of them that are aligned in latitude, in longitude, sorry, in, like, as you say, vertically, in longitude. Now, these kind of like shallow parts could be just a bunch of spots that are spread out more or less evenly, so they kind of like consistently occult the whole disk, like a different part of the disk, and as they come in and out, they don't have a very strong impact. So yeah, those things can happen.
Yeah.
So I was particularly curious as to maybe perhaps if when you think about processing language and
Yeah. So it's so interesting because we are now in both my projects, the one that I have, with my students at George Mason University, and the other one that we have here with the Earth observation data, I'm thinking about the same thing, NLP and image processing. It's like, it's the major theme here. And for, I'll start with the Earth observation, which is the other FDL challenge. There, it's a little bit more straightforward in the idea that it's not that we are applying NLP techniques to the images, but rather can we identify NLP data sets to marry with the images. So that's different. And the way I'm thinking of doing that, maybe it can be applied here or not, is to pull out from the literature, from NASA's literature, but not just, from the papers that have been published that used Earth observation data, to pull out those papers and parse those through text, and then marry those with the images that have actually been used for publication, right? And in this way, to get a better tagging of the images or better labeling of the images based on the findings that have been published in the literature. So I don't know if this is something interesting to apply here. So that's one project. So again, think about, have there been any publications about stellar magnetograms that we can parse and take the NLP out of them and then marry them back to the actual images that have been used, right, for in those publications. The second one, I think it's actually more interesting and can be applied here. So in the second project that with my students, we are actually looking, so we reduced actually all the data sets that we have to looking at symbolic languages. So languages that are represented by different symbols. And can we parse those ones using image processing? So we are looking at the actual shape of the symbol as in an image. And then can we look at the actual text and again marry the natural language processing with the image processing over there. Again, we are using several tools, so I'm trying to go really fast with this so that I can apply this to FTL as well. And looking mostly at basically at similarities, right? And if we are looking in natural language processing at how often I'll call these n-grams. N-grams stand for, let's say, words, although in symbolic languages, we don't really have words, but we have groups of symbols, right? So can we look at how frequent do certain n-grams show up together, or how in a sentence, but which is basically aspatial, so it doesn't refer to any spatiality. But can we also look at how they show up in a page? Because in symbolic languages, we are talking about writing on tablets, so it matters if they are written on top or on the bottom, right? So we are looking at different similarity measures in the actual image, right? And similarity measures in terms of language processing. So.
What similarity measures are you using?
So that's a good question. So I'm looking at co-occurrences. So how often do they occur? Either they are next to each other, they are one step apart, so there is another n-gram between them, or 2 steps apart, or how many steps apart they are over there, and how often they show up in. So if we have many tablets, right, many of these images, how often do they show up in the same context, so in the same tablet? Okay, so that's another similarity. So it's basically in the normal terms, if we are looking, if we are thinking about the normal English languages, how often do they show up in the same sentence? How often do they show up in the same paragraph? How often do they show up in the same document? When we are looking into an image, so let's say that we have like symbols, so we read this as an image, then we are looking at how close they are in their positioning, one with respect to each other. So we can look at that in with respect to von Neumann or Moore neighborhood. So if they are close to each other in diagonal, or they are close to each other, you know, if we are looking like in a chess kind of board.
So for example, take one of our light curves, right?
Yeah.
In some ways, you can think that the unit of that light curve is a rotation, or 2 rotations, or something like this, that has to do with the lifetime of the spot as it comes twice around, or something like this. So we could take, for example, a light curve, which is a sequence like this, and we break it into words, which are going to be unique curves on that unique sections of that curve, and these words may be repeated, or may be far from each other or close to each other. So if you try to think about this, perhaps, how would you?
Yeah, so that's actually a pretty neat way to look at this. So instead of looking at light curves, can we look, so as we had with the, with the sun magnetogram, right, where we have the pixels and we have the matrix, right? Do we have matrices of numbers for?
We can simulate those. We can simulate like a surface of a star, but the data and how this stellar surface will produce a light curve, but our data are one-dimensional. So it's almost like it's as if you had like either like a spoken language where everything is timed, like like you're taking a phrase that has no two-dimensional relationship with each other, but you have still some form of sequence of words that are pieced together in time. So I think our light curves will be more like the spoken. If you will do this with the spoken language in some way, or with the written language.
That's really neat. Yeah. So actually, what we can do is, but these come repetitive, right? So there is some repetition there because they move around. So there are 3 types of writing, 3 ways in which writing has developed. So one, it's when you are looking at writing from left to right as we are writing, then right to left as, let's say, in Hebrew and maybe Arabic. And then there is the writing called boustrophodon, which is like a serpent. So it's left to right, right to left to right. So it goes like this, right? So I'm thinking of the light curves more like this boustrophodon, right? Because it goes like this, like a serpent, right? That's pretty neat. Now, just like you're saying, it's one-dimensional data, so we're not concerned about, how they are related to each other in space, but we are concerned about how they are related to each other in the context. And now what we need to do is to define the context. What exactly is a sentence, or what exactly is a paragraph in terms of time, right? In the time series of the light curve, right? So if this is repetitive, I would say that one rotation could be 1 page, right? The second rotation, the second page, and we can analyze this like that, right? that's kind of neat. And yeah. And in one page, let's say if inside one rotation, we can look at all the dips and how they are positioned with each other, and we can parse these as, you know, like each mod of those modulations can be an n-gram. Oh, that's super neat. And we can run some pretty, you know, one reason why I chose for this other project symbolic languages, and particularly languages that we don't understand, that have not been deciphered yet, is because I'm trying to work with agnostic data, right? So it's data that we don't bias it with our, you know, understanding that if I read horse, I understand horse. No, if I read horse, I understand HORSE, I understand just 5 symbols, right? In which none of them is repeated with each other, but how do they relate to other symbols? So yeah.
So how would you, like, if we were just going to sit down with this data right now and just look at it this way, what kind of technique would you use to try to understand? What is the phone, like the how do you say, the conceptual unit, the word, so you have you have something that is a bunch of characters, right?
Yes.
And you can say, well, okay, this is Chinese, so each character is a single word. But you could also, without knowing anything about this, you can say, well, no, this is maybe it's written in a phonetic language, so as accumulation of symbols is actually a word. And so, but you don't know how many are, and which ones are words, and which ones are together. There are not spaces or markings that are obvious spaces.
That's exactly the data I'm working with right now. So it's the rongo, linear A, you know, there is all the scripts that have not been deciphered yet. So yeah, that's
so how do you like, what would be the first step to do something like this?
Statistical analysis, basically. First thing, how much, which are the frequent words, what is how can you find repetitions? First, look at the repetitions, spot anomalies versus the patterns, you know, in the data. So plain statistical analysis, like n-gram frequency or symbol frequency. So how often do you have modularities versus how often do you have the dips? Can we fit a distribution into those? So usually in languages, we fit the zip distribution, which is a power law with the power of -1. So that's the test that it's telling us that this is not random, right? That this is actually intentional, right? That there is a process behind it, right? So yeah, so that's the very first thing that we do. We are looking at all statistical properties. The second thing that we did is a method that is specific for natural language processing, which is called topic modeling. So what topic modeling is looking at is that these frequencies in different documents, and it assigns probabilities for how often you can find that n-gram into a certain document, right? And how...
What's the name of this again?
Topic modeling. So
topic modeling.
Yeah. So topic modeling is very interesting because, again, it's agnostic with respect to the language. It doesn't, so computers don't understand exactly what these words mean. But they do understand, you know, how often you can find them in different contexts. And you define these contexts in either probabilistically or either based on, you know, statistical properties.
I'm hearing.
Yeah. So
I'm taking notes as we speak.
Just give me data. I'll run all the code that I have on that, and it will be so interesting. Yeah. So the second thing is topic modeling, and then we are also doing unsupervised learning. So we are looking at if we can identify clusters. So we are looking like at K-means type of neighbor thing. If we can identify clusters of symbols, right, or of n-grams in different ways. And another thing we have been looking at is the entropy. So we calculated the entropy of the language based again on the word frequencies, and to show, you know, how close or how different languages are from each other, which is, again, it's agnostic. It doesn't mean they don't understand, you know, the words, the frequencies. They are just looking at, or the meaning of the words, right? They are just looking at at different frequencies, and what's the probability of that symbol or that engram to show up, in
and what will entropy tell you?
So a high entropy basically tells you that there is a lot of randomness and disorder, right? While a lower entropy, it shows that it's actually something that has, again, a process that is going on behind it. And another thing that we want to do in the future, we haven't done it yet because we also just started, is entropy-based clustering. It's something that the linguists in computational linguistics, they also use. So you can do the same idea, if you have clustering or supervised learning, but instead of looking, I don't know what, different similarity features, you are looking at the entropy of the symbols.
This is fascinating. So let's say we have that curve. How would you do this in that? Like, we will just break it in some unit of time and create a dictionary of these patterns, and for a given light curve, start comparing how frequent they are, and
so I would so basically, if these are show like waves, right? That they're like waves with different amplitudes and different, I don't remember what you call the how wide they are, right? So they are basically, the data is unidimensional, but these waves are two-dimensional, right?
Yes.
More or less.
Yeah. I mean, it's time versus in reality, it's time versus an intensity.
Yeah. So, but you can break them into waves that are similar, right? Based on the amplitude and the width, right? And so it's sinusoidal, right? So you can break it like that.
Oh, and so break it on the nodes.
Yeah.
Like take a sequence, find crossings on the nodes in some way, and break those as the pattern that you're going to match.
Yeah, so I guess you can break it in several ways, right? You can have smaller breaks or the full break into...
Now, will this become like prohibitively expensive? Is there an optimal way of doing this, in the sense that, let's say we have a light curve that is 3 years long, and potentially this means that we will have, let's say, if rotation is 1 month, then in 3 years we have 36 words, right? For a star. And then we have, let's say, 10,000 to 50,000 stars, right?
Okay.
Now, each star, I guess you can consider as a page of text. And maybe there are other stars that have different pages of text. Are you going to try to compare all with all, or is there anything that you will do first to kind of like reduce the dimensionality of this?
So that's a good question. So I would actually consider each star as a separate document. And I would consider the one rotation of that star as one page in the document, right? And and inside the rotation of the star, I would consider the n-grams, with the waves, with the dips, right? So inside one rotation, I would consider how many n-grams I have that are n-grams that are similar to each other versus the n-grams that are dissimilar to each other. And then, so basically, if I have 10,000 documents, with each document having basically, I don't know, it depends on the rotation of the stars, right? So they'll have a different number of pages.
Yeah, let's say between 50, let's say between no more than 100 pages.
Right, between 50 and 100 pages. And each page in turn would also have, between, I don't know, 10 to 50 maybe words.
No. If you want to do a single rotation, it will have maybe 1 or 2 wiggles maximum.
1 or 2 wiggles, okay.
Yeah. That's what I was thinking, the page or the word to be longer, to have more stuff going on.
Yes.
But yeah.
So I guess you can do, so how many, so you can do, I guess, several rotations for one page, right? And those several rotations would correspond to, so for how much is the time length for these 10,000 stars?
Let's say 3 years.
For 3 years. Oh wow! So you can do, but it also depends on how fast.
But one rotation is let's say 30 days. So 3 years is about.
Sorry, you broke up a little.
Yeah, sorry. So let's say there are.
Andres?
Sorry.
Okay.
I'm back.
Sorry, I lost you for the last minute.
Yes,
so.
yes. I realized when, because I know exactly when. So so let's say there are in a single time series of these 3 years, there is going to be about 50 pages.
Okay.
Or between 20 and 50 pages, let's say.
Yeah.
And then we have 10,000 of those to 50,000 of those. So then, is there an optimal way of doing this pattern matching? And
no, so the way this works in with text mining, so you would import all the documents. So you import all 10,000 documents with all the pages, and at first you don't look at the pages at all. You just import the whole document, right? And you create what's called a term matrix. So you define this as, for each document, which are the words, the n-grams, and how often they show up in each of these documents. And then you look at this matrix to see how sparse it is or not, right? And if it's really sparse, you get rid of the empty space as much as you can, and you are left with a more meaningful but with a smaller matrix. And it's that matrix that you start processing basically for, let's say, clustering, for topic modeling, and so on.
And what if you have this, like, let's say this language is written in script, and you have different people writing scripts, so the A looks slightly different in one than in the other. So there is do you use like some form of similarity to say, oh, this is the same character, or this is not the same character?
Yeah, that's a really good question. So that's pure image processing, and that's why we are doing image processing of the symbols. But usually you already know, so when these symbols, they are already coded in Unicode, basically. So regardless of how you handwrite them, they have just one unique Unicode. Now, the way I would do here, because you can't really transform these into Unicodes, I would look at how different so I do like a full statistical analysis and see how different they are from each other, and then I would bin them, right? So and then I would create bins, and then I say, okay, this bin is for symbol A, this bin is for symbol B, this bin,
Okie doke. I think that's basically it for now.
Oh my gosh, you gave me so many ideas. Can I also get some of their data to play with? I don't need all 10,000. Although, how big is it? Like time series of 10,000?
I mean, we will. Yeah. There is I mean, we can just give you access to our project in the Google Cloud, so you have access to those. I think that the whole database is about 3 terabytes.
Okay.
But these are all stars, even those that don't have words.
Okay.
So these are 200,000 stars, out of which not all of them will be out of which a lot of them will be empty pages. So one of the things that we were discussing that needs to happen first is that we need to make sure that our pages don't have gibberish. So So I don't know how big will be that subset will be, but it's definitely something that we can share with you for sure.
Oh, please, yes, I would love to do this. I will I'll take the time, to transform those in different n-grams, and I'll just run the whole algorithm that I already have, for text mining. So.
Okay, I mean, we can do it with one single star quickly, early on the project, and
well,
you can...
I would need more than one, maybe 10 or a few. Like give me 10 stars, or something like that. So yeah.
Okay, awesome, Anamaria. Thank you so much.
Oh my gosh, this is awesome. Exciting.
Yes, it is pretty exciting. Okay,
Oh, yeah.
awesome.
I get full of ideas anytime, every time I talk to you. So
I
like,
know. Well, I mean, that's the same with me. So,
yeah, awesome.
okay, well, thank you so much,
Okay,
Leslie.
okay, yeah, I'll see
No,
you
no, I don't
tomorrow.
need to, just a second. I just
Yeah.
need to record. I'm going to stop the recording.